Good morning. I am Juan Carlos Trujillo from the Research Lucentia Research Group from the University of Alicante, and I'm going to summarize one research that we are dealing related to understanding large language models via mechanistic interpretability. Well, we all know about the large language models such as GPT, Gamma, and so on, that cause a huge revolution. We are, of course, now working with them, especially with text summarizing or even code generation and so on. So, according to OpenAI, of course, there are three main factors that we all know already that affect the performance of large language models, LLMs. Is the compute during training, the data set size, and parameters. The number of parameters, the amount of data, and the time of computing, all of them dramatically affects the test loss of any LLM. Well, we all know already that are absolutely black boxes mainly because of the large number of parameters and the complex internal interactions, which is a serious safety concern. Actually, the first talk today was about the problem about the explainability of artificial intelligence, even more the explainability of LLMs, and also, according to the details talk yesterday, that there are safety concerns about the black boxes and even more with the LLMs. For example, if we use GPT in a very simple way, with a very simple prompt like this one, if we repeat poem, 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 GPT can easily leak sensitive data that it shouldn't be. And the question is why? Why LLMs are recovering sensitive data, and what's happening underneath? This is the hypothesis that we're working with. And the motivation of our work is that we are applying mechanistic interpretability. That is a method that intends to make a reverse engineering of neural networks behaviors in terms of human understandable components. So the idea is, let's try to understand how these neural networks work, and in this case, this will help us to find out unexpected behavior of the LLMs, such as the previous example. So if we are able to understand what's happening, we may be able to prevent unexpected behavior. So this is a research that we are dealing, as I told you, in our research group, especially together with two colleagues, Jorge Garcia and Alejandro Mate. And basically, the work I'm going to present here is based on the paper that we presented last May in the STAS conference, which is how does GPT-2 predict acronyms? I will go in further detail in a minute. And in 2 weeks, we will present in the IGCAI in Jeju, we will present how to detect and understanding vulnerabilities in large language models. So we are basically doing mechanistic interpretability in order to find out what's happening underneath LLMs in a concrete task. So, sorry. So as I told you, I'm going to focus here in this work, which is how does GPT-2 predict acronyms, extracting and understanding a circuit via mechanistic interpretability. And I'm going to focus first on the introduction, then the methodology, then the results, and finally the conclusions. In order to find out what's happening underneath LLMs, we need to focus on a specific task. In this particular case, we have focused on how GPT-2 small performs acronym prediction. And to the best of our knowledge, and according to the literature up to now, any prediction was based on predicting one single token. So what's going to happen in the next and in the following token. So in this work, is the first work in which we deal with predicting multiple tokens. So the prediction of multiple tokens. Actually, this word can be easily applied. We are already doing so. We are applying to any multi-token prediction task performed by many LLMs. So let us just introduce how this, in which mainly research issues is this based. We reframe a transformer-based model such as LLMs, which currently all current LLMs are based on transformer-based models. So we reframe as residual streams, where we consider all the components of LLMs as components that read and write in this residual stream. And we consider the components composed by attention heads and also multi-layer perception. However, according to our experience that you may find further detail in the paper, we will focus on only attention heads because the MLMs are not relevant for this specific task. Okay, so the goal here is try to understand the set of components, a circuit that is carrying out the task. In this particular case, the task of predicting the acronyms. So the methodology is based on 3 main steps. First of all, we build a synthetic data set that elicits the behavior of the task of study. I would like to point out here that we don't retrain any LLM. Okay, we don't retrain. We just generate the synthetic data set that we need to test and to find out how LLM is working inside in order to predict this task. And then we apply a series of activation patching, as I will show you in a minute, a set of activation patchings to identify the relevant components that are active, that are working for predict something. And then, of course, we made an analysis of understanding what's happening and what's happening with these components. First of all, we are covering the task here of predicting 3-letter acronyms. So then we build a synthetic data set, and the pattern, the template of this synthetic data set is composed as follows. We start with the word T, and then we have capital letter 1, the rest of the word 1, so capital letter, the rest of the first word, second capital letter, the rest of the second word, and capital letter, and the rest of the capital letter. And these A1, A2, A3 are the acronyms to be predicted. Then the one critical issue in this methodology is the activation patching that we generate. So this, the activation patching enables us to carefully trace the information flow and allow us to find out the critical components on a specific task. As we can see here, we have a clean prompt, which is the core prompt. We need to find out to predict the third acronym, and this is the clean prompt. And we also build corrupted prompts. In this particular case, for example, this is a corrupted prompt for the next word. So this I will show you in a minute the different kinds of corruption activation patching. So the idea here is that we find out the critical component on the right of the clean prompt, and then the patching, the activation of a given component degrades the performance. This means that this particular component is absolutely relevant for the task. And how we work, if we replace the activation, in this particular case, if we replace this activation head, the performance will dramatically decrease. So therefore, this means that this activation component is critical for the task. So we have 3 types of corruption for this particular task, which is we have the original statement with the original sentence, and we need to predict the third acronym. So we corrupt the current word. So we made a synthetic data with a corrupted word. We also corrupt previous words. So we have the same part of the acronym, and we corrupt the previous already found words. And we also corrupt the previous letters. So regarding the acronym, so we corrupt the correct acronyms. And also we have a third pattern, which is all corruptions all together. So this is the main pattern. We build the synthetic data to test the LLM. And then, thanks to these activation patches, as I showed you in a slide before, replacing, using these corrupted patterns and the correct prompts, show us what are the main components that absolutely decrease the performance of the LLM. In this particular case, we have 4 attention heads that absolutely decrease the performance, which means that these attention heads are relevant for the task that we want to predict. The third part of the methodology is to analyze the corresponding attention pattern, the attention heads that we have previously detected that are relevant for our task. So there are further details in the paper, but basically we analyze the learning weights, the logic output, and also the previous attention heads, so what's happening previously with the previous attention heads in the different previous layers. And after a care analysis, we found out what's happening for this particular task. So we are able to detect what are the main attention heads having impact in this particular task. And if we remove every component outside the circuit, the detected circuit, if we remove, we can observe that the performance is preserved, which means that we work correctly and the detected attention heads were absolutely those that are relevant for the task that we are going that we want to predict. So which means that we were able to find out what are the main parts of the LLMs in a specific task. In this particular case, we located 4 attention heads in the different layers, 8, 10, 9, and 11. These 4 attention layers that we showed before are the ones we call them letter mover heads. What are the attention heads that allow us to predict the next acronym? So are those relevant? In the three acronym prediction. Well, letter mover heads use the previous predicted letter to attempt the correct token position. So this is what we are able to find out here. And there is also information that this information is also propagated from the token I-1 to the next token to be predicted in a set of using previous heads that we make a correct analysis on what's happening for the different heads. Well, the idea here is that thanks to the mechanistic interpretability, we were able to find out what are the different attention heads that are part of that are taking part on the prediction here. We also found out some curious issues here. For example, we found that these attention heads, these letter mover heads, are able to derive positional information from attention probabilities. So they are able to derive if positional information that is crucial for predicting the task. Due to causal masking, the attention paid to the beginning of the sequence also generally decreases the destination token position. And this can be used to infer the position of the destination token, as we can see here. And this is the experiment with all the clean entrance and all the different 3 corrupted patterns that templates that I showed you before. So we can see that for all the tokens, the behavior is doing the same. So the conclusion is, as I started, that to the best of our knowledge, this is the first work in predicting multi-tokens with LLMs. And we are working pretty much on this research and on several works and taking into consideration the mechanistic interpretability to enable us to understand what's happening with large language models. Of course, we have to focus on a specific task in order to be able to find out with the batching, finding out what are the main attention heads. Well, and this is you can access to the archive as well paper, and also with the GitHub with all the experiments about the code and the experiments that we have accomplished, not only for this work, but also for the work to be presented in 2 weeks' time, that will be based on mechanistic interpretability. And we are not only with this specific task, that we are getting good results in trying to find out what's happening underneath LLMs, which is very complex. It's affecting when we apply, for example, as we have seen before, in medical issues. There are several domains that we absolutely need to find out and to explain how these big monsters have taken several decisions.
Little differences in the vector, like the values in the high-dimensional vector. Very small differences could give extremely different result. So nonsensical outputs. You look at the embedding phase.
We configured the embedding phase, but we didn't make a deep analysis on corrupting the embedding layer, as you mentioned.
Yeah.
Just we corrupted the inputs. Yeah. But if you can please send me that.
I try to find it. Try to look for it.
Okay. All right. I will appreciate, because you're right. We pretty much focus on the corruption of the inputs.
Yes.
But that's right. That it depends on the embedded as well.
Yeah. They call it something like lost. They make the joke of lost in translation. All right. From translating from the tokens to the vectors, they get lost in this translation. Anyway.
Okay. I think
lost in translation was part of the lost in translation.
Do you remember the author? Sorry. No. Oh, okay.
I think it was people from OpenAI.
OpenAI.
I think it was, yeah. But the authors were, if not all, there were authors of OpenAI.
It's Salesforce.
Which one?
Salesforce.
Salesforce.
Yeah. It could be.
Brian McCann.
Could be.
Yeah. Learn in translation, contextualize word vectors. Maybe it's the debate.
It's about the value. The vector value.
It's something that would maybe not. I'll try again.
Thank you. I will have a look at it. It's quite interesting.
Too many things that are published every day. We get lost.
All right. Okay. I'm sorry. Let me just point out something. I read a news came to me that if any of you is taking a plane today, it seems that there's been a problem with Azure. I don't know if you are aware of that. A news came to me, so I don't know if you are aware of. That is something critical with the planes, especially if you have to go to travel road. Do you hear about that?
I'm not traveling.
Do you hear about that?
Yeah.
Giant cloud strike.
Yeah. I read something about them. Yeah. But that's mostly my text. So, yeah. Mostly there's no problem with the train.
We have a position committee on next Monday, and it came to me, that several members of the committee are stuck in Brazil because they cannot fly today.
Yeah. Many airports are stuck. Many airports. The US and everywhere.
It seems more in the US and
the US, actually Barcelona, I think too.
Yeah, in all over the world. Okay, so sorry. That's a question to be sure. Okay. Thank you. Sí, pasa que si presentáis,
Me tengo que estar con la capa, ¿no?
no fastidio.
Yo me he puesto ahora de cerca y voy, cuando me toque esto, voy
Claro, yo qué sé, pero bueno, yo quiero vengo, yo sé,
también me gusta.
yo subo porque he seguido, claro, no soy también con el que dejaré el sueldo de atención. Por ejemplo, no estoy trabajando mucho en las características para el más y logro que afecta a la concentración.
Tengo que ir, pero es interesante.
Se va a ver.
De acuerdo, y eso
Bien. Muy bien, vale. Venga.
Igualmente, puede ser de otros seis, ustedes pueden saber, vale, de acuerdo,
Yo de hecho, además es que yo, no te acuerdas, no fue tú y yo que nos carteamos un par de correos. No nos carteamos un par de correos hace tiempo que te escribí yo para ver si nos veíamos.
Sí, me dice. Sí.
Porque
Muchas gracias a todos. Desconectamos ya. Vale, un saludo final. ¿No? ¿Quieres finalizar? Sí, finalizo.